Hi, this is your screencast for section 2.7. Section 2.7 is on VSEPR and bond hybridization. The learning objective is based on the relationship between Lewis diagrams, VSEPR theory, bond orders, and bond polarity. A, explain structural properties of molecules, and B, explain electron properties of molecules. So VSEPR stands for valence shell electron pair repulsion, and it deals with the different shapes of molecules. The essential knowledge is molecular geometry, bond angles, polar molecules, hybridization, and sigma and pi bonds. Now, when we covered this in class, there were several different shapes for molecular geometry. You only need to focus on the ones that are covered in this review. So the first one, CH4, this structure is called the tetrahedral. Got to get a pen here. Okay, so this shape's called the tetrahedral. You can read that, okay? So the tetrahedral is when you have four atoms bonded to the center atom, and this hybridization is based on sp3 hybridization. The way you figure out hybridization is you look and see how many effective pairs are coming off of the center atom. So an effective pair is a single bond, a double bond, a triple bond, or a lone pair. So if we have four effective pairs, in this case we have four single bonds, that's sp3 hybridization. So when you have four bonds, that's called tetrahedral. Another thing you want to know is the bond angle associated with sp3 hybridization, and that's 109.5 degrees. So it's 109.5 degrees between this bond angle for these outer atoms. Another thing with this is you want to know sigma bonds and pi bonds. A sigma bond is a single bond. A pi bond would be another double or triple bond. So every type of bond is a sigma bond, and a pi bond is anything extra, like the extra bond in the double or the two extra bonds in the triple. We'll talk about that more later. Now, along with this sp3 hybridization, when you have four bonds, it's called tetrahedral. But in the case of something like NH3, you have three bonds, like so, and a lone pair. This is still considered sp3 hybridization, but this shape is called trigonal pyramidal. The bond angle for this between the hydrogens would be slightly less than 109.5. You don't have to know the exact bond angle. When they correct the AP test, they give you a little bit of leeway. And it's usually within a range of like 10 degrees. So if you just said everything that has sp3 hybridization has a bond angle of 109.5 degrees, you'll be okay. Technically, it's 107.5 for this bond angle. And what happens is the lone pair of electrons, they tend to occupy more space because they're only localized to one atom. So they have more range of motion. So what that does is it squeezes these bonds together a little bit and decreases the bond angle. So you don't need to know the exact bond angle, but you do want to understand the concept that lone pairs of electrons take up more space and decrease the bond angle between the other atoms. Another example of this is water. Where you have two bonds and two lone pairs. This is still sp3 hybridization, still based on the bond angle of 109.5. The bond angle is even less. It's 104.5 between the hydrogens, and because the two lone pairs take up more space. But if you just simply said 109.5 for this, you'd be in good shape too. The name of this shape is bent. It's a bent structure when you have 2 bonds and 2 lone pairs on the center atom. So all those structures are based on sp3 hybridization. The next one is sp2 hybridization. And this is an example of one right here, this boron trichloride. The bond angles here are 120 degrees. And this shape, if you have 3 bonds and no lone pairs on the center, that shape is called trigonal planar. So sometimes there's some confusion between trigonal planar and trigonal pyramidal. Trigonal planar is when we have no lone pairs of electrons on the center atom. Trigonal pyramidal, like we saw in the previous slide, has a lone pair on the center atom, like NH3. So the bond angle here is based on 120 degrees. Another example of this would be the SO2 molecule, which has 2 double bonds and a lone pair. This is still considered sp2 hybridization because we have 3 effective pairs on this sulfur. The bond angle is still based on 120, but the bond angle between the oxygens would be slightly less than 120 because the lone pairs of electrons are taking up more space. In this case, we have 2 sigma bonds and 2 pi bonds. Every type of bond is a sigma bond, and then anything extra, you can think of anything extra as a pi bond. So in a double bond, you'd have 1 sigma and 1 pi. 1 sigma and 1 pi. So this structure has 2 sigma bonds and 2 pi bonds. If you have a triple bond, like in the case of nitrogen, it's connected by a strong triple bond. This would be 1 sigma bond and 2 pi bonds. The next one is carbon dioxide, and this is the last structure you need to know about. This is sp hybridization, and the bond angle here is 180 degrees, and this is considered linear, a linear shape. And this carbon dioxide, just like the SO2 on the previous slide, has 2 sigmas and 2 pi bonds. And those are all the shapes that you need to know about. You don't need to worry about sp3d or sp3d2 hybridization. And I won't worry about the other shapes of molecules like octahedral or seesaw. Those shapes never show up on the AP exam. It's always going to be the ones that we talked about in the review. So that's it for today. Have a great day.